So today I want to talk about our experience with Julia. So I will mainly show some lessons learned that we should think twice before moving forward. And by we, I mean a bunch of people at my institute that are part of the group. And yes, what is the question that we want to answer, or what are the topics that we are interested in? So basically, we focus not on ice, not anymore. We focus on water and carbon. So, and what I mean by that is that we use physical models to simulate these processes, such as photosynthesis, carbon allocation, wood, litter, root. So all these processes that are happening in plants, we study them via equations. So, and these equations will output some quantities that can be measured afterwards. So these measurements that we take at the end are like evapotranspiration, carbon rates, and the vegetation health, like NDVI. So this we call targets. So once you have your models, what you want to have at the end is a comparison between the model output and these observations that you will measure. So your equations usually have parameters. So, and you want to parameterize this, okay? You want to optimize these parameters. Why? Because these parameters usually are site dependent, okay? And when I say sites, so the sites are the observations. In this case, we are using FlossNet sites around the globe, which collect all this data, okay? So this is the data that we want to integrate into our models. More than that, so we will use remote sensing data as well to simulate all these processes. So this data, which I am calling forcing, is time dependent. So we have years and years of data for all these variables. And for parameters, I have static data. So this data is the one that I will use later on to optimize these parameters. So my goal is twofold. So I want first to do optimizations per site. So that means that I will optimize these parameters in each location individually. In a sense, I will be overfitting, right? So once I optimize parameters on one site, I cannot transfer those values to other sites. So the goal that we endeavor here with Julia was to build a framework able to specialize for parameters that can be retrieved in a spatial matter, okay? So this is, in this plot, I show how this data looks like. So the black dots are the observations that you will usually have, and the blue line is the output from the simulation in this site. And the red line, of course, is the result that we get from this model that can specialize in the spatial domain. So, but how do we solve this problem? Well, we learned Julia. So, but when we learn Julia, we need to make some decisions on the model and design. And you will see some resemblance here to speedy weather. Apparently, we converge on the ideas in every model framework. So for us, it consists of 4 elements plus 1. So at the end, I will mention what is this one. So first, we define a model, and we try the definition of this model to be as simple as possible for users as well as for scientists. So we start with the definition of this model in our land ecosystem, okay? And then just to say, for this approach, for this process, for this physics process, I can define my own model. In this case, I call it my example. And usually, when you have these kind of models, you will have a parameter, right? But from physics or from observations, you usually have a given value. So what we do in this definition, we say, I have some default values, but then I can attach the units for that. I can put a short description, and I can also encode the bounds. Okay? So we wanted to have something simple to read, so just not like equations, but more like natural language. Okay? So this is the best we could come up with it. Then forcing, so each one of these models will have a forcing. So the forcing means that you have some input variables for this model, and these ones can be constant or can be arrays as well. LAN is also a collection of named tuples. I mean, as you can see, the syntax is named tuples. So you have your model. Input is forcing, which is a named tuple. LAN is also a named tuple, but this named tuple can also contain named tuples. Okay? So basically, you have your model, your forcing, and your bucket. We call our bucket LAN because we will put everything in there. So once you do a computation, everything will go into LAN. And helpers is something generic that will be shared across components. Yeah. And the plus one is basically compute. So compute is basically you define your model, and once you define your model, you have your forcing, your LAN. You can say, OK, I need this variable from this one and from that one, like diagnostics, fluxes. And then you do some calculation, like calculate variables, like a new value for your variable. And then you say, now, pack that new value into my diagnostics field, or my pools, or my fluxes. And that's it. So you want to create a new physical model approach. You do these steps. And then you can plug in and play with this anywhere in your workflow. And yeah, one of the lessons that we learned the hard way is, yeah, we should aim from the beginning for 0 allocations. And types, like all the types need to be known. So for our framework, we make sure that we have always 0 allocations and all the types are known. And once you have this, you can have all your models run in sequence. So you usually pass a tuple of models in the right sequence, and then you run them all. And because everything is 0 allocating, it's quite cool. So what do we want with this? So we can do automatic differentiation, and we are able to construct a complete workflow to optimize our parameters in space. So basically, we have the static variables. In this case, our new model for these parameters is a neural network, which will output new parameters. You will have your forcing. You will have your terrestrial ecosystem model, the collection of all models. You have your predictions. Then you calculate the loss. But because you can do AD, you can calculate gradients. You use those gradients. You multiply by the Jacobian. And then you can update the weights of the neural network. And then you repeat and repeat and repeat and optimize. So in conclusion, we have these lessons here learned so that we are able to optimize these parameters in space. So I would like to love and hear your thoughts on this. And please don't hesitate to ask or talk to me after this. Thank you a lot.
Thanks, Lazaro.
Yep.
We have time for a very quick question.
Cool.
I have a question. So maybe can you get back to the slide of the neural network that you said? So what is the result, or what do you want to put inside the neural network itself? Just the data, or?
So the input to the neural network is data, yes. are all these static variables that I mentioned at the beginning.
And the output is?
In the output, it will be new model parameters. So it will be a collection of parameters that go into your equations. Okay?
Okay, and
So because I want to optimize for all of them at the same time. So when I do these static variables, I'm passing a matrix that will contain values for each site. Okay?
Okay.
So it's a batch of observations
Okay, so you just want to find the parameter of that site.
of that batch of sites, yes.
Okay, okay,
Okay.
that's clear. Okay.
You're next.
Cool. So moving on. Applause for Lazaro, please.
Thank you.